Welcome to Maths with EJD. Today, I'll continue my videos on matrices as I consider eigenvalues and eigenvectors. What are these concepts? They are really important and central to the idea of matrices. Okay, so talking about eigenvalues, right? As it rightly sounds, they are talking about values. And that is why eigenvalues are scalar values associated with a linear transformation or a matrix. They represent how transformation stretches or compresses space along a particular direction. In simpler terms, eigenvalues indicate the scaling factor by which a matrix transforms space. Now, a real life example is what you see, the picture you see to your left. So think of a rubber band being stretched or compressed when pulled in a specific direction. So if you stretch a rubber band in a specific direction, the factor by which the rubber band stretches or compresses is analogous to eigenvalue. So if you're stretching the rubber band makes the size double, so you can say the eigenvalue is +2. But if you actually have like a ball of a compressible ball like that, you press it and it shrinks to half its size, then you can say that the eigenvalue is -2. So that's the kind of idea eigenvalue represents. So of course, let's talk about eigenvectors. As you already know, a vector talks about direction, right? Both magnitude and direction. So eigenvalue is more like the magnitude, while eigenvector is like the direction in which that thing goes. So eigenvectors are the corresponding vectors to eigenvalues. So as you compress or stretch that rubber we talked about the other time, so the direction in which it stretches or is compressed is actually it talks about your eigenvector. So they represent the directions along which linear transformation only stretches or compresses without changing the direction. All right. So a very good example, of course, is still using the rubber band example. So if you stretch the rubber band, the direction in which the rubber stretches is your eigenvector, or the direction in which it is compressed is actually your eigenvector. And then, of course, we can talk about this spinning top. Consider a spinning top while it rotates. So it's more like you're rotating something like a circular disc. So while it rotates, right, there are certain directions or axes along which the top doesn't change its orientation. This stable axis can be thought of as eigenvectors. So it's like as the thing is spinning, right, there are certain directions that will be maintained even while that spinning is taking place. So those are the eigenvectors. But the easier example is a rubber example. As you stretch your rubber, you know, the direction in which it stretches is what the eigenvector represents. Okay, so let's talk about the mathematical formulation of eigenvectors and eigenvalues. Now, the eigenvalues of a square matrix are obtained by solving the characteristic equation a minus lambda I equals 0. So the eigenvalues of a square matrix are obtained by solving the characteristic equation. Now, before now, we've talked about the idea of characteristic equation when I was talking about Cayley-Hamilton theorem. Okay, so and this is exactly what the characteristic equation looks like. So the determinant of a matrix minus lambda I. Lambda is just a scalar quantity, while I is the unit matrix corresponding to the matrix A. So if matrix A is 2 by 2, of course, it has to be square, right? So you can only talk about eigenvectors for square matrices and eigenvalues and eigenvectors for square matrices. So if A is 2 by 2, then I has to be a 2 by 2 unit matrix. So if you find the determinant of A minus lambda and equate to 0, the equation resulting from that is called the characteristic equation. So the solution to that characteristic equation is what gives you the eigenvalues. And while the eigenvectors associated with eigenvalue are computed solving for V in this equation. So, here now, this is your A minus lambda I, now multiplied by a particular vector V. So, which is, which is actually a column vector, right? Like that normal vector of, say, X, Y, Z, depending on the kind of matrix you're considering. So, when you solve for V in this expression, you actually get your eigenvectors. So that is the purpose of this video. So let's see some practical stuff. Okay, so look at example one. We have a matrix, a 2 by 2 matrix. So consider the matrix A, which is 3, 1, 1, 3. Okay, of course, since we know that the eigenvalues are obtained when we solve the characteristic equation, absolute value, determinant of A minus lambda I equals 0. Okay, so A minus lambda I simply means you have 3, 1, 1, 3 minus lambda I is 1, 0, 0, 1. So multiplied by lambda. So lambda 0, 0, lambda, right? So that you have 3 minus lambda, 3 minus lambda, 1 minus 0, 1, 1 minus 0 again, 1. 3 minus lambda is 3 minus lambda. You see, that's how that came about. And the next thing you want to do is to find the determinant of the left-hand side. Of course, to find the determinant of this, it's to say 3 minus lambda into 3 minus lambda minus 1 times 1. That's 1, of course, and all of that is equal to 0. So we try to expand this. So 3 times 3 is 9. 3 times minus lambda, that's minus 3 lambda. Minus lambda times 3, that's minus 3 lambda. Minus lambda times minus lambda is plus lambda squared minus 1 equals 0. Okay, so now you have lambda squared. You have lambda squared minus 6 lambda, 9 minus 1, that's plus 8 equals 0. And that's exactly why we have this expression. Okay, so we just have to solve that quadratic expression for lambda, and then we get our eigenvalues. So how do we do that? Of course, I don't think it's a new thing, right? So you have lambda squared minus 6 lambda plus 8 equals 0. So the rule is you need two numbers which are multiplied will give you the product of 1 and 8. So so you have 1 times 8, that's 8, right? You need two numbers multiply, you get 8. But those two, the same two numbers, when you add those two numbers, you get minus 6. When you add those two numbers, you get minus 6. And those two numbers would usually be coming from 8. So in what ways can you get 6 from 8? That's to be 4 and 2. 4 times 2 is 8. But then we need this to be negative, right? So the only way is to make this minus 2 and minus 4 and minus 2, right? So minus 4 times minus 2 will give you 8. Minus 4 plus minus 2 will give you minus 4 minus 2, that's minus 6. So now minus 4 and minus 2 are good for that. So in that case, since you have established that minus 4 and minus 2 will be fine, so we can just go ahead and say that expression, so this expression now is the same thing as lambda squared minus 2 lambda minus 4 lambda plus 8 equals 0, all right? So we have lambda, you can factorize lambda into lambda minus 2. Here you can factorize minus 4, so minus 4 into lambda minus 2. Because minus is outside, this plus becomes minus inside here, so we have that to be 0. So we have lambda minus 2 into lambda minus 4, and that is equal to 0. So you have lambda is either 2 or 4, and that is why the determinant, the eigenvalues are 4 and 2. So of course, it doesn't matter which one you call lambda 1 or lambda 2. Lambda 2 can be lambda 1 and 4 can be lambda 2. It doesn't matter at all. So here we are taking lambda 1 to be 4. And lambda 2, we are taking that as 2. So with that, we can go on. So now we have found the eigenvalues, basically. So the eigenvalues are found. But then we don't need just the eigenvalues. We also need the eigenvectors. So let's see how we can get the eigenvectors. So that example still continues. So in this case now, the interesting thing is that since we got two eigenvalues, lambda, which are 4 and 2. So 4, it means that if you imagine the example of a rubber band, so it means you have stretched the rubber such that it has increased it has become quadrupled, like it has increased in length 4 times, or in another case, it has increased in length 2 times. So for each of 4 and 2, you are going to have different eigenvalues, eigenvectors. So for eigenvalue 4, you're going to have an eigenvector. For eigenvalue 2, you're going to have another eigenvector. So for each eigenvalue, you have a corresponding eigenvector. Okay, so let's go ahead. So for the matrix A with eigenvalue lambda 1 equals 4, right? Remember the matrix A is 3, 1, 1, 3, all right? So you need to find A minus lambda. Don't forget, for us to find eigenvectors, we actually need to, this is a kind of expression. We have A minus lambda I multiplied by V equals 0. So now we are looking for this V. So in this place now, we are basically looking for A minus lambda I. But then we are talking about lambda 1, which is 4. So with that now, we have A minus lambda 1i. So that means you have 3, 1, 1, 3 minus lambda 1, which is 4, right? I, that is 4, 0, 0, 4. And then you have 3 minus 4 here, 1 minus 0, 1 minus 0, 3 minus 4. So you have minus 1, 1, 1 minus 1, like that. Okay, so with that now, so we are looking for V1, which corresponds to lambda 1. So let V1 be xy, be the eigenvector corresponding to lambda 1, okay? So then you have to solve this expression, a minus lambda lambda 1i rather, multiplied by V1 is this. So a minus lambda I is this expression that we got. So we have minus 1, 1, 1 minus 1. Then V1 is xy, and all of that is equal to 0. Don't forget, we are trying to solve a minus lambda I multiplied by v equals 0. Okay, that's what we're actually solving. So this 0 now is what you have on the right hand side. Okay, so if you work this out based on matrix multiplication, right? You know, this is 2 rows, so it means you have to write xy twice, xy, xy. So for the first one, you have minus 1, 1, and the second one, you have 1 minus 1, and all this is equal to 0, 0, and then you have minus x plus y equals 0, or x minus y equals 0. So you see minus x plus y equals 0 and x minus y equals 0. Okay, now from each of those, right, you can simply say that, you know, minus x plus y equals 0. That simply means that y is equal to x. If you also do this, if you transfer y to the other side, that one also give you y equal to x. So you need only one of this to determine what the eigenvector is going to be. Now, when it comes to eigenvectors, you need your intuition, you know, because depending on the situation, two people do not have to get the same eigenvalues. I mean, eigenvectors, I mean. It must get the same eigenvalues, but not necessarily the same eigenvectors, okay? So you'll understand that when we finish with this particular video. Now, if you look at that thing now, we already saw that, you know, we have x plus y equals 0, you know, and we had x minus y equals 0. Either way, if you evaluate, you end up getting y equals x. For any one you pick, you get y equals x. So what that simply tells you is that whatever the value of x is, the value of y will also be. So since y equals x, so, and it's always good we start from, I mean, usually you want to start with 1. So any non-vector scalar of multiple 1, 1, because when x is 1, y is automatically 1. So that's why you have 1, 1 like this. So when x is 2, y will be 2 also, and so on and so forth. And that is why we say any non-zero scalar multiple of 1, 1 is an eigenvector corresponding to lambda 1. Okay? So that's the eigenvector corresponding to lambda 1. So you have lambda 1 to be 4, and then you have lambda 1 is 4, right? And you have v1 to be 1, 1. So this is the eigenvalue, and this is the eigenvector in that case. All right, so we go ahead again and we look for the eigenvalue corresponding to the second eigenvector corresponding to the second eigenvalue too. So for the matrix A with eigenvalue lambda 2 equals 2 now. So again, don't forget, we are looking for a minus lambda I. You know, this is what we want to solve, equals 0, right? So a minus lambda 2i, that's, don't forget again, you have 3, 1, 1, 3, minus lambda 2 is 2. So 2, so you have 2, 0, 0, 2 again. So 3, so that 3 minus 2 is what you have here. 1 minus 0, 1 minus 0, 3 minus 2. So 3 minus 2 is 1. So you have 1 all through. So it's a matrix of all ones. Okay. In that case now, so we now say let V2, which we are looking for, be xy. Let it be the eigenvector corresponding to lambda 2. So we have a minus lambda 2i multiplied by V2 equals a minus lambda 2i is 1, 1, 1, 1. Then multiplied by xy, all of that equal to 0. Okay. So, of course, you already know that is going to be xy, xy, and then that's 1, 1, 1, 1, you know, like that. And that is equal to 0, 0. And all that is simply x plus y equals 0, x plus y equals 0. So same thing. So basically here you see that y is equal to minus x in each case. Either way, anyhow you pick it, y is equal to minus x. So, and that's what we're going to see in the next slide. So coming to the next slide, you see what exactly I said. So this gives us the system of equations, x plus y equal to 0 or x plus y equal to 0. So it's just the same thing. So in this case, solving the system yields y equals minus x, all right? So any non-scalar multiple of 1 minus 1 is an eigenvector corresponding to lambda 2. Why? Because y equals minus x. When x is 1, y is automatically minus 1. When x is 2, y is automatically minus 2, and so on and so forth. So any non-zero scalar multiple of 1 minus 1 is an eigenvector corresponding to lambda 2. All right. So that's a 2 by 2 situation. Can we look at a 3 by 3 case, which is like our example 2? So consider the matrix 4, 1, 1, 1, 4, 1, 1, 1, 4. So the characteristic equation is given by a minus the determinant of a minus lambda I equals 0. Of course, and that will be 4 minus lambda 1, 1. Because this is actually 4, 1, 1, 1, 4, 1, 1, 1, 4 minus lambda I. So that's lambda 0, 0, 0, lambda 0, 0, 0, lambda. So you subtract 4 minus lambda, you have this, then that's 1 minus 0. So you see everything is on the diagonal, 4 minus lambda again, and then 4 minus lambda, like that. So that's why we have all that. So, of course, before now, we already knew that right, that is about looking for determinants so that